Morning guys. So today we'll be doing the third video of AC, that is alternating current. So till now you would have understood the basic idea of what an alternating current is, how it is represented and how it is actually present in our daily life, and what is RMS voltage, RMS current, what is peak voltage, what is peak current, etc. That is the introduction part actually, right? From here, that is from today's video, you are getting into the alternating current as per your CBSE board section to the core of the chapter. Okay, so make sure you understand, or you study the complete derivations. From here it will be purely derivations. Okay, and from AC chapter, in the when I say numerical questions are very easy, right? Whereas the derivations are straight away derivations are asked. Okay, so let's move on with the chapter, that is AC, and the topic which we are going to deal with today is AC in a resistive circuit. That is a circuit which has only resistance, right? So the circuit will look like this, a simple circuit. So you have an AC supply, then you are having a resistance R, right? It is straight away connected. And let's say you have a key also, right? Let's say this is your key. Okay, let's make this one as key. Okay, so you have a circuit like this, right? And due to the supply, say I current is flowing through the resistor, right? So the input, right, this is your input. Let's say that input I am taking as voltage. Okay, that is given by epsilon is equal to epsilon naught sine omega t. This much we have learned earlier, right? So this is the expression, and what and all was E and E naught. E naught is the peak voltage, right? Peak voltage of the AC, and whereas E or epsilon, which you have written, is called instantaneous. Instantaneous means the EMF or voltage at the time interval t, right? So this is instantaneous voltage, and epsilon naught is the peak voltage. Now some of your textbook, as far as I can see, in most of the NCERT quest textbook, it has been written that you are mentioning in place of epsilon it is V, and in place of epsilon naught it is Vm sine omega t. Both are same. Okay, just the representation has been changed, right? V is equal to Vm sine omega t, where Vm is the peak voltage, V is the instantaneous voltage, right? So both expressions are same, guys, just the representation has been changed. That's it. Clear? I hope this much is clear. Right, let's move on. Right, so we are giving an input voltage, right? So after that, let's move on with the derivation. Right, now we have learned that in the chapter waves, right? We have the representation of a wave. Remember, it is y. Y means in the displacement is in the y direction, is equal to am sine omega t. Remember, we have studied an expression like that. Let's compare this equation and the equation we just wrote, that is epsilon is equal to epsilon naught sine omega t, right? So that means what was AM in our wave equation was the amplitude. Remember, amplitude of the wave is represented by AM, right? If this was the wave, so this is AM, right? Similarly, so this peak EMF or peak voltage can also be termed as what? Voltage amplitude, right? It's also called voltage amplitude. Which one? This epsilon naught, because it is quite same. Clear? Right. So similarly, don't we have the expression for current also? Remember, we had the expression like I is equal to I naught sine omega t. So that means this I naught can be also called what? Current amplitude. Can be also called as current amplitude. Clear? Simple. And in our textbook or so many of the textbooks, this equation is also written in this form, right? That is I is equal to Im sine omega t, where Im is the peak current or current amplitude. Just this representation is different. Both are correct. Clear? And both current and our voltage are in sinusoidal form. This much clear. I just want to make the clarification regarding the written forms of these equation in your NCERT textbook. Okay, let's move on with the portion. Right, now we just know that if there is a circuit like that, that is, we wrote a resistive circuit, right? We drew a resistive circuit, right? So as per that, what will be the equation for epsilon or the EMF with respect to the diagram? I can write it as E is equal to what? I into R, right? Or I is the current which has been flowing in the circuit. Then can't I write this E? I will write it as E naught sine omega t, right? So if I write this section, right, that means E naught sine omega t is epsilon naught that has been written in the earlier side, right? So what I am going to bring this R in the denominator of this section, that is epsilon naught by R sine omega t is equal to I. Now this epsilon naught by R, I can write it as like this, I naught sine omega t, right? Then that is equal to I, right? So make this one as a box, right? So that means we gave an input of epsilon is equal to epsilon not sine omega t. That was the input, right? That is, input is in a sinusoidal form or alternative form, right? This is the expression or the diagram for epsilon or the voltage. I gave an input of voltage, right, which is in the sinusoidal form, right, or in the alternating form. And what type of current generated in that circuit due to that? The current generated is also in the sinusoidal form or the alternating form. Right? That is a basic conclusion. That is, if alternating voltage is applied in a circuit which has only resistor, then the current flowing through that circuit also will be alternating current. Right, it will be also alternating in nature. It's something very simple which you know by yourself, right? So we are just explaining it in a mathematical way. Clear? Now, how can I represent current and voltage in the graphical way? Right, that is the second point which we are going to deal today. Right, so this is a first point, that is expression of current and voltage in the AC or when an AC is in a resistive circuit. Now I am going to change, or the second point which we are going to do is graphical representation. Graphical representation. Right. How I am going to graphically represent that voltage and current in a resistive circuit. See, even if we know that voltage and current are sinusoidal, right? And we saw that both of them, what was the expression? It was what? Epsilon is equal to epsilon naught sine omega t. And what was current? I is equal to I naught sine omega t, right? Both of the expressions are quite similar, or I can say that both are in same phase, right? They are same phase, right, as you can say as per the equation. But see, epsilon naught and I naught's value are not same, because see, I naught is equal to epsilon naught by R, right? Current is equal to voltage by resistance. Now, as the value of R increases, this value goes on decreasing, that is epsilon naught by R decreases, or I can say definitely current's value is less than voltage value, because voltage is divided by some quantity to get current, right? So current's value is always less than what? EMF. That's why when you plot a graph, you know, it's very easy, which is like this. Right, let's say I'm drawing a graph for EMF like this. Right, this is the graph for EMF 0. This is the peak. Sorry, let's make it okay, sorry, another color came up. Okay, so this is the peak, so let's make it as epsilon naught. But when I draw the diagram for current, the magnitude of I naught is less, but it's of the same phase. Clear? So this is I naught. Clear? This point is pi. This is 2 pi, right? Clear? 3 pi and goes on. This is omega t. Clear? This is for EMF or current. This is the representation or graphical representation of AC current and voltage, right? That is, and what is the average of EMF for one cycle? We know average of current, right, is equal to 0. Similarly, average of EMF is also, or voltage is also 0, because they are forming a sinusoidal form. Clear? Simple? Right. But now comes the third point which we have to discuss. That is power of a resistive circuit. Right? So these are all points. If you are writing the notes, make sure you are writing it as a point wise notes as because it is very easy to study in that form. Clear? Now, as you can see, current for one cycle is 0. Similarly, EMF for a cycle is also 0. So you would think that power we have written till many classes we have learned power is equal to voltage and current product. So power has to be 0, right? But no, power is not equal to 0. Now why I am saying so? See, when we study about power which is associated with resistor, power dissipation in resistor is in the form of what? Heat. Right? And heat, usually we write the expression as what? I squared RT. Right? It is I squared RT. That means heat is proportional to what? Square of the current. And current as it is positive for or small time interval. Then I squared will be also a positive quantity. Right? So heat when, or energy or power when I am dealing, it is never equal to 0. Clear? Now we'll prove that. How? I'm damn sure that it is not equal to 0. We'll prove that now. Okay. Now we are going for derivation. We know that E epsilon is equal to epsilon naught sine omega t. Right. Similarly, what is I? I is equal to I naught sine omega t. Right. Then what is instantaneous power? Power will be epsilon naught into I or Vi. Right. So I can write it as epsilon naught sine omega t into I naught sine omega t. Right. Now I am going to bring some terms closer. That is epsilon naught I naught. I am bringing it closer. And then it is sine squared omega t. Right. Now that is power. That is instantaneous power. When you are asked what is average power, what would you do? You have to take the formula, right? You have been taught what is the formula for any function f of t. The average is written as integral 0 to t time interval f of t dt whole divided by integral 0 to t dt. Right? Now here what is my question is average of power. Right? So it will be integral 0 to t p of t dt divided by integral 0 to t gt. Clear? Now what is integral? This factor, this is t, right? And I have to apply upper limit and lower limit 0 to t, right? Now let's move on. Integral, so this denominator section I am going to write it as 1 by t, right? T minus 0. And expression integration of 0 to t power will be, we just wrote it as epsilon naught I naught sine squared omega t dt. Clear? Right? Then this epsilon naught and I naught is a constant term. I am going to bring it outside. Epsilon naught I naught divided by t integral 0 to t sine squared omega t dt. I have taught you the expression for sine squared omega t in terms of cos. I can write it as 1 minus cos 2 omega t whole divided by 2. Right? Integration 0 to t. right? Moving on, that is equal to epsilon naught I naught by 2t, right? Integral 0 to t cos 2 omega t. Now, after integrating epsilon naught I naught by 2t, right, I'm going to integrate 1 and there is a dt, okay? There is a dt, I missed out it. dt for this entire expression. So, it is 0 to t 1 dt minus integral 0 to t cos 2 omega t dt, right? Now I just told you for one entire time period cos or sine functions integration value is 0, right? I told you guys why it is etc. I have explained earlier itself, right? So now I'm going to write it as epsilon naught I naught by 2t. Then there is only this integration of 1 is t, so it is t, right? Now that is upper limit minus lower limit, you will get t itself, you cancel out, you will get the answer as epsilon naught I naught by 2, right? Clear? So that means what is the average power for one cycle? It is epsilon naught I naught by for one cycle or for infinity. Now after finding the value of average power, see, you can see I can write this or equation in a different way, right? That is, suppose this entire term, if I'm going to change the value of say epsilon, I'm going to write that in terms of, let's say this is epsilon, right? I'm writing epsilon in terms of current. So can't I write this as I naught, right, into R? So it becomes I naught into R into I naught divided by 2. I'm just changing, guys. It's okay if you don't, but I will bring a very wonderful form of equation. That's why I'm doing it. So this is equal to I naught squared R divided by 2, right? Now I am going to change, see, writing this equation in this form, 2 whole squared into R, right? This is the same value here, right? So what do you mean by this? I naught by root 2, that is our RMS current, remember? So I can write this as IRMS squared into R. So average power can also be written in the form of RMS current, that is IRMS squared into R. That's another expression for average power. So right, so it is either this expression or this. Both are correct. Okay. After finishing off our power or average power derivation for a purely resistive circuit, now we are going for the fourth topic, which is phasor diagram. See, this is a new section, guys. You would have never heard or seen about it, right? So phasor diagram is actually, see, every VI relationship, that is voltage current relationship, can be depicted in pictorial way, right? One is graphical method, which we have studied earlier, right? Graphical method. Now the other is phasor, right? By drawing phasor diagram. Now phasor diagram consists of a phasor, which is actually a vector which is capable of rotating, right? That is capable of rotating with an velocity of omega, angular velocity of omega. I hope you don't understand anything. See, I have drawn it earlier, right? But I think I have to draw a bigger figure. Let's draw the figure better. Suppose, let's say this is my axis, right? I'm drawing a larger graph, right? This is 0, this is 30, 60, 90, 120, then 150, and this is 180, right? Here this is 210, right? 240, 270, then 300, then 330, and this is 360, right? Now see, this is my 30 degree, right? right? Say this is an this graph is for an quantity A, right? Now quantity A at 30 degrees having this much amplitude, right? Now I am going, this is axis is two axes I have drawn for phasor. I am going to draw a vector for it. Now this, see, this is 30-degree, right? So I draw a line like this, right, which is of 30-degree, right? Now extend this line like this, right? Now see, this is the corresponding amplitude, right, for this point. I can say this is the point, this is the point corresponding to this point, right? So now this is the vector for A. Clear? Right? If you don't understand, I can draw this again. For 60-degree, I am dropping a line like this. Right? Now this is the point here. So for phasor also, which is the angle here? 60. So 60 is here. Right? I will draw a line like this. This is for 60-degree. Right? And corresponding to this point of our graph, 60, I have this point in our phasor, and this depicts the amplitude of A at that angle 60-degree. Clear? Clear? Similarly for 90, right? So this for 90, say this is my angle point 90. So this is the meeting point. So this is depicting the phasor for that. Clear? So when I draw the entire diagram for the corresponding phasor diagram, it will look like this, right? For a complete circle, right? This will be for 30-degree, this is 60, 90, like that, different angle for different wave, and this will be corresponding for this wave. This 90 degrees for this, 60 will be this 30, right? This is 30, 60, 90, like that. Say I will draw or show how. Now this entire thing I can show you by an already existing animated video. See, this is how our actual graph and the phasor diagram. This is a graphical representation. This is the graphical representation. This is our phasor diagram. See, as the graph moves, corresponding to that the vector is moving, right? That means if our graph is like this, right, for a velocity or for an angle, say omega t1, correspondingly I can draw a phasor like this. Yeah, for omega t2, like that I can draw and depict it, and then this entire vector, if I join, it will look like a circle, right? This is phasor diagram, right? Now let's just draw the same for our resistor. Clear? Now how for resistor, guys? Right, now for that, first I have to draw the graph for our voltage and current. I'm extremely sorry, it doesn't look good, right? So let's move. Okay, this is my voltage current graph, right? This is for EMF, and for current it is less amplitude, less. So this is EMF or E naught, which is the maximum, or this is I naught, right? This is omega t, this axis, right? This is 180, this is 360. So this will be for 90-degree, right? So let's say this point, say for any omega t1, right? Omega t1. So for that I am going to depict a phasor. So for omega t1 I have to plot a line like this, omega t1, right? Now for current, see, for current, this is my, let's take another point, this one, right? This is current, right? I'm bringing the line here. So this point is for our vertical component or vertical value of current. Now this is EMF, bring that line, right? So this point is for EMF. Hope this much is clear. right? So this is epsilon and this is I. Sorry, this is I, right? And see, this epsilon can be written as epsilon naught sine omega t1, right? Similarly, I is equal to I naught sine omega t1. Right. Similarly, if you want to take another time interval, this is omega t2. Right. Similarly, I have to bring omega t2. I have to draw another phasor vector like this. And the amplitude of that vector, this point will be for current, this point for EMF like this. Right, and the equation of for those EMF and current will be epsilon naught sine omega t2. Current will be epsilon naught, sorry, I naught sine omega t2 like that. This is how you represent the phasor diagram. Clear? Easy? Right, now we'll move on with the next topic. Let's say at least a little part can be completed regarding our inductive circuit. Start with the next small top, not small, portion of inductive AC circuit. That is, in place of resistor we are going to consider circuit where we are going to have only an inductor. So this is my supply, this is our inductor, right? And let's say this is key, right? This is our inductor, right? The current is flowing I, right? So we have the input voltage, let's say, which is epsilon is equal to epsilon naught sine omega t, right? Now, and this is an inductor L, right? Now we know due to the inductor and there is no resistors here also, then there will be one source EMF, which is this one, and there will be an induced EMF or self-induced EMF here, right? Clear? Now this, as the current is changing, therefore there will be a magnetic flux associated with the current, right? Then according to the Faraday's Lenz's law, right, or you can say Lenz's law, whenever there is a change in flux, a current will be induced or an EMF will be induced in the inductor. That is, there is a self-induced EMF, right, which will oppose a change which is causing in it, right? So when you apply a KVL or the in the circuit, it will be voltage, or I can say EMF, that is a supply, plus the back EMF. Let's say I am writing it as 0, E, which is the induced EMF. I am writing it like this, guys, because so that both expression doesn't confuse it. So that by KVL both the sum should be equal to 0. Now this E, let's say it is E. Now what is induced EMF? It is minus L di by dt, right? So minus L di by dt is equal to 0, right? This much is clear, right? Now what is E? We have written as E naught sine omega t minus L di by dt is equal to 0, right? Simple, right? Now let's change the expression, guys. Right, so I am going to bring di in one side, right? So di will be equal to what? Epsilon naught sine omega t dt divided by, right, then there will be a L, right? Just rearranging it. Clear? Now we have want the expression of current only, right? We gave voltage, we want expression for current. So that means if di is given, you can find the current by integrating it, right? So by integrating the both sides, it will be integral 0 to I di, so I, okay, is equal to integral, right? So integral epsilon naught sine omega t dt whole divided by L. Simple, right? Now what can I do? What is integral di I to I? It is I is equal to epsilon naught by L is a common or constant term, integral sine omega t dt. Integrating sine omega t, it is minus cos omega t by omega, right? So it is, I can, sorry, so I can write this as into 0 epsilon naught by L minus cos omega t by omega, right? Plus C constant, because I have not introduced any what limits here, Oh, epsilon naught L omega. This one I am bringing. So it is writing, I am writing it as minus, I am going to bring it outside. So it is cos omega t plus C, right? That is our current, right? I am taking a small rubber, guys, because the minus here. Okay, now this is the expression for current, right? So I am removing this constant term, right? Because constant is 0 because as a source voltage oscillates, right, symmetrically about 0. Therefore the current should also oscillating about 0. So I can just remove the C. It doesn't make any much difference, right? Now, so I got an expression for current, and usually what is the current's equation? It is I is equal to I naught cos omega t or sin omega t. This is sinusoidal, right? It can be either sin or cos. Waveform you have learned, right? So I can write this one in this form. So that means I naught is equal to epsilon naught by L omega, or there is a minus here, right? Clear? This much is clear, right? So that means the usually what is current? Current is equal to voltage by resistance. So this L omega is in the place of resistance, right? So for an inductor, right, there is a small resistance, right? The small resistance offered by the inductor, that is known as impedance, right? Impedance of a inductor circuit, and that is equal to L omega, that, and the representation is XL, right? XL is equal to L omega. So I naught is usually written as epsilon naught by XL in the case of inductor circuit in place of R, because there is no resistor, right? So small resistance which is offered by the inductor is known as inductive impedance, right? Clear? So epsilon naught by XL, or XL is written as L omega. Now this is a minus component, right? I can also write this minus in the form of, right, I is equal to I naught sine omega t minus 90 degree, or I can write it as pi by 2, right? So this is the final expression of current, right? What is the expression of EMF? Because E is equal to epsilon naught sine omega t, whereas current, it is I is equal to I naught sine omega t minus pi by 2. Just leave it like that, and what is the significance of this equation will be dealt in the next class. Okay.